let's run the first simulation. So let me introduce you what we're going to do. So we're going to use a Poisson solver. We have this domain, okay, and square domain 111, okay, and we have these boundary conditions 0, 0, 0, and here we have this boundary condition depends in the distance. So we're going to show you also how to implement non-uniform boundary conditions. It's very straightforward, and this is the equation we solve. Okay, and we're going to do it in different domains. So we're going to see the influence on the mesh and the solution. We're going to use this back quality mesh, and you're going to see why it's important not controlling some options in the input files. And this problem have an analytical solution, this one that you see here. Okay, so we can compare here and see the influence or gradient schemes, depletion schemes in your final solution. So let's run this case. Okay, so we already have the meshes. We converted in the previous video. We show you how to do conversion. So let's do, okay, we're in Laplace cavity. Okay, let's go to the first case, the exa mesh, the perfect mesh. And here you have the instructions. So open that one, you will see the steps. You'll need to repeat the mesh, but if you haven't done, you can do it. So you have it here. Remember, always the mesh, you go into grid, this directory grid, and run this command, and then go back to run the solver and everything. So just to remind you, the organization is the structure of a case. So you have this folder, and here you have the boundary conditions. You have here the name of the variables that you are solving. In this case, the solver Fluid Poisson would solve a variable named t. Okay, so as you go to Navier-Stokes, you are going to have u, p, k, x, and whatever. So here you give the boundary conditions. You have here, okay, the header. When you have the exclamation point, means that this is a comment. So everything comments, you can add it like that. And the notation used here, the data structure is JSON format. Okay, so if you don't know what is that, just look in the internet, you will find that. But it's a very easy to use format. Okay, very easy to understand. So here you give a name. This is the name coming from the mesh. Whatever measure that you use, how you call those surfaces, the boundary surfaces, that is the name that you get. So we're getting exactly the same names. So if you want to fix a value, remember that in our domain, we have this 0 in the walls, bottom, left, right. See that in this case, this is how you set this. In the top, we have this boundary condition, extremities. So it's a user-defined dash. You have also user-defined Neumann and stuff like that. So see that you have sign. So you get your mathematical function and just put it here. Okay, then you go to button, okay, 0, and then we have front and back. We call it void. Okay, so this is a 2D simulation. Okay, so you can have it. If you have it 3D, you are going to put it here also 0, 0. But if you want to work 2D, call it void. And this is how you initialize. Initialization also, you can have non-uniform initialization in the same style as in here. So this is how you set up your boundary conditions. Then we have grid. Here you need to touch anything. How you convert it from OpenFOAM, that information is fine. Then you go into physical, and here you're going to have constants and things like that. So in this solver, you have ρ and mu, okay, diffusivity and rho, okay, to constant. Rho is the one that you're going to multiply your time derivative. Mu, you multiply the Laplacian, and this is the interpolation. Also here you can access the interpolation of these properties. Okay, so the default interpolation that we use are harmonic, but you can change it to linear, and there are some other methods. Okay, see that is commented. Okay, you can go to the source code and look for this variable, and you will see where it's implemented. And then post-prod, this is the last part where we have the solution. For the moment now it's empty, okay, nothing here. So here you have the solution. Here you're going to have monitors like residual forces, stuff like that. And here you're going to have the fields in BTK. So previously we convert the mesh in BTK format. You have it there. And then in settings, you have all the numerics. You have 4 input files. For this case, probably you in some cases you are going to have more because you need to set some monitors, but this is the basic setup. Okay, so as you open these files, the first one that you see, we're going to is simulation controls. Okay, so these are runtime parameters. So Fluid Poisson, we're going to run in a steady mode. Okay, so as we are going to run in a steady, you have here, see that you have tiny steps. So you can put here any number. The solver will do iterative marching one iteration at a time. So it doesn't matter what number you put here, it will run. Then here you have the maximum number of iterations, or your maximum time. And these options are related to the saving frequency, okay? So see here that we put 1, we're going to save every single solution. And these are the last files that you want to keep. So you want to keep the last 100 or the last the last 5 files. Is up to you, okay? Then also here we're putting the option to save gradients if you want. Okay, by default this is not saved, but in this case I want to save it. So every variable that you have in the solver you can access. Okay, so if you have more variables you access like this. Then this is to control residuals. One thing that here we're showing you the compulsory options. Okay, so if something is commented, it's not compulsory, it's optional. So this is optional. So if I want I can comment it, but I want to save my gradient. These are optional, so this is just to change the residuals, okay, how they are saved, okay, the frequency and the amount of information I want to see on the screen. And that's all. This one is telling you to restart from the last one if you want to do a restart. Then you go to discretization. Here you choose the discretization for each variable that you have in your equation. So remember that in the Laplace, in Poisson, you have time derivatives, and then you have the Laplacian, okay, you have gradient. So this is steady, there is no time derivative. So you don't see here the definition, how to compute gradients. Okay, so here we're using greenhouse. You have also this square implemented. Then for the diffusion term, you have this method implemented. Okay, so this is the interesting part, the part that we're pushing a lot, because this strongly depends. The mesh quality strong. The method that you choose strongly depends in the mesh quality. Then see here that tiny skin steady. Okay, this variable that you see here is related to the diffusive. So this is experimental. It is commented. Do not use it for the time being. Or if you want to check the source code, and you will see what it's doing, and the number of corrections, okay, due to mesh non-orthogonality to improve gradients. So this is basically to improve gradients. So this is a perfect mesh. So you don't need, you put 0, it will be okay. Later we're going to see when we move to tetra back quality meshes, you're going to see the effect of that. So this is how you choose. Okay, so every term that you have in the equation, you need to declare something here. So if you don't put, if you forget to put something, or if you put something wrong, the solver will stop and it will let you know that, okay, you have a problem. I will show you later. Linear solvers, and this is probably the most interesting part for us, because we're using here PETSC. PETSC is a very efficient solver, okay, to solve large linear system. So here you can access all the variables in PETSC. So I'm not going into details, go to the documentation, okay? So, but exactly the same names that you give in PETSC, you put it here. So we're not showing all the options here. So this is the compulsory option, but there are many more options related to the solver. Okay, so here you give the solver, the preconditioner, the absolute tolerance and relative tolerance, and maximum number of iterations, okay? All this related to PETSC. I invite you to read the PETSC documentation. And in the case that here you use a steady state, you're going to read this input file. And basically here just you are given the residual control, okay, for the steady solution. So you give here the residual. So you are going to stop when your initial residuals reach this tolerance level, and on the relaxation factor for each variable. So here we have u of t, you have u, you are going to have another entry like this with up, whatever, with the on the relaxation. So it's important that see that the residual here in this case is a little bit larger than this one, okay? This is the linear solver, okay? The final residual, this is the initial residual, okay? Just to make that difference. So this is how you define a case. So at this point, let me run. Okay, so remember that you have readme here and you have the instructions. So to run in serial, you can run like this or like this. It's up to you. Okay, so I will go like this without the MPI. Okay, so you see that is It's telling me that settings, Fluvio control. Okay, so for the time being, okay, so here I have an old version, okay, of Fluvio. So let me go back. Okay, so we are here. Okay, so let me go here. That was an old version of Fluvio, and here. Okay, and this is the solver I need to run. Fluvio. I go here, run, and see that it's running. So you have in screen the message, everything, so initialization, everything, and see that you have the variable that you are solving, number of iteration, the linear solver, final residual, and it's doing 2 iterations. Okay, so here, see that your initial residual reach the tolerance that you define in your dictionary, in your input dictionary. You go here, settings, you define here steady state, this, and it is stopping. So now that you have a solution, is you go here into postprod fields, see here that you have 0, 1, 2. Okay, for each iteration you have a solution. This is binary format of Fluvio. If you want to visualize this, you need to convert it to the format, the BTK format that you can open with PyReview. To do that one, here you will have another command. See here that Fluvio fields, okay, can be serial parallel. So here you are just converting the fields. So you are starting from the field 1 to the field 2, and this is a skip. Okay, 1 means every field. If you put 2, will be like 1, 3, 5. Okay, so I can go like this. Okay, so save everything into BTK format. And now see that in postprod BTK fields, see that you have all the fields here. And now you can open PyReview and you can open those files. So important when you convert that using this command, you are converting just the inner cells. You are not converting the boundary patches. You can also convert the boundary patches if you need to. Okay, so initial conditions, and then you iterate and you get the solution. Okay, and a very nice solution. Just recall these slides, you will see that this is the field, but then I will show you how to add the analytical solution. So as I mentioned, that you are saving only the inner cells. If you want to save the boundary patches, you can go like this. You have this command Fluvio boundary fields. Okay, number of processors 1. You want from, let's say, 0 to 2. Skip field 1, the same idea, minus BTK, and now you give minus boundary. And you can give a list of all boundaries. So left, right, back, front, top, bottom. Okay, these are the names coming from the mesh. So if you do this, see that you are doing the conversion, and now in the BTK fields, see that you have these new files, BTK files. These are just the boundary fields. Okay, so now you can open that, and you have all the information, inner cells and boundary cells. Okay, so you see that open top, and see that this is just the top patch. Okay, you have it there, and you have the information there that you have there. Okay, so this is if you need to have the patches. If you don't need those patches, open the internal field. So that's all. Okay, this is how we run. Okay, so the theory that we're using, everything that you're going to see here in this dictionary that is the most important, discretization, is the standard theory of the finite volume method. Okay, any of the most popular books is the finite volume method. You will have this this theory explain it there. And just to show you that, here we have the paper. Okay, you go there and you are going to have here the references. So this is the preliminary presentation of the solver, but as you go to the references here, see that here you have many papers and many books. Okay, that theory that we're using, it is explaining in all these references here. Okay, so you have all these books. It's a very standard theory, is the finite volume method. Okay, so let's say up to, let's say here 12, from 1 to 12 is the finite volume theory that we're using. This is related to PET-C, the linear solvers. Okay, so this is it. If you want to clean the case, you have those scripts there. So clean sh, and I don't want to clean the grid. You have this one also that will clean the grid. I don't want to clean it. So just to show you that, for instance, you forget to input an auction, see that I'm commenting gradients. If you try to run, it will complain. See that it's telling you that this key is not defined, okay? And for instance, if you make a mistake like this, will tell you that that doesn't exist. These are the options that you have available, okay? So this is how we run this case. Let me rerun again. Okay, we're running this case in serial now. Then the next video will be how to run it in parallel. So just to show you a complete post-processing, okay? So we have this one. Let me convert the fields, okay? And I will launch PataView, okay? We have the solution, everything. And one thing that I want to point out that you will find in this case is this file. This is the state of PataView, okay? So if I go here, load state, here you need to specify the directory. So I want to search in this directory, and it will open and see that we have, this is already as a thought that I did in PataView is the one you can do it, all this operation manually. So you see that this is your solution, okay? So let's look at first at T. This is temperature, and this is the analytical solution, okay? Here. So you see that we have a very good agreement, okay? So see here that we use the calculator to compute the analytical solution, okay, here. So we put the equation here. Okay, and this is what we're looking. Now we can compare these two solutions. You can do this subtraction, but see that we have a very good agreement. So for instance, you want to see the mesh, you can access that here. Okay, so be careful because here we're looking at the volume mesh. Okay, so you are plotting all the cells. So if you have very large meshes, instead of doing like this, it's better to put a cut plane, okay, just to visualize the mesh in those cells. So be careful, okay. Volume mesh, and if you want to see, for instance, the boundary patches, again, come here and post-prep BTK fields. Okay, I need to convert those patches. Okay, so we did it previously. So let's see here, you go here and let me convert again all those patches. You have the patch information, PataView. Okay, and let me do a step-by-step manually, okay? So if you open the state, PataView will load everything, will do it automatically. Let me show you how to do it manually. So you go here. So Fluvio fields is the internal mesh. So see here that you have your Fluvio fields. Okay, this is the internal mesh. If you want to load, for instance, the top patch, select there, and you will have the top patch, okay? There, if you want to load, I don't know, the left wall, you have it there. Okay, so you can choose everything and you will have the solution. Okay, then you can access the slides, everything there. Okay, and to compute the, for instance, you want to compute the analytical solution, you get there in your mesh, put the calculator and put the expression there. Okay, it's relatively easy. So all the post-processing for the moment we do it in PataView, okay? So if you want to sample in a point, a line, everything is done in PataView. You can also use the Python library accessing BTK, okay? But it's easier for the moment as you are a beginner. It's easier just to use the PataView to do that. So this is how you run a case. I hope you follow the steps. It's not that difficult. You have to remember always you have this README files with instructions. So let's go and let's move to the tetra meshes, okay? So the steps are basically the same. So we go to Laplace tetra and I can run here the solver. So I already have the mesh, already have the setup of the input files. So see that it is running now in 4 iterations, okay? So we're in tetra, and here again, what we do is just adjust the numerics according to the mesh that we are using in this case. So let me open this. So see the numerics, we have this method. We're using now 2 non-orthogonal correction because here is not a perfect orthogonal mesh. And what else? Linear solvers, tolerances, everything. And just to show you also something else, that in post-prod here, remember you have the binary files with the solution in Fluvio format here when after you convert it. So let me erase this one. And as you go here, monitors, you have residuals. Okay, so as you open that file, these are the residuals of the simulation. So then you can go new plot and you can plot that information. Okay, so see that we go logarithmic scale, and here you have scale residuals on scale residuals. It's up to you. Usually it's better to look at the scale residuals. In this folder also you will find, for instance, you are computing forces, you are going to find the coefficients here, CLCD or the forces. Okay, so now that we run, we have a solution. Okay, let me show you how to convert this one. So I will go here, let me convert. So in this case, it ran 4 iterations. So again, look at here, you have the steps, and let me compare the Fluvio field. So let me go from 1 to 5. Okay, we have the solution. Now let me launch Parabeam. And I will load the state. Okay, this one to do things automatically. So search in this directory and see that you have here, this is Fluvio solution in our Tetra mesh. Okay, look at here that we're looking at this slice. Okay, so you put there the 3D mesh, it will be a little bit slow, and this is your analytical solution. Okay, let me erase, and here you can compare. Okay, so analytical solution and numerical solution. But what is interesting is the gradient. So now that we don't have that orthogonal mesh, okay, we have no orthogonality, okay, those triangles you see here, that this will influence how you approximate gradients. It's better to look at gradient information. So as you look at here, gradients, see the numerical gradients, but also we have access to the analytical gradient. So as you go there, this is your analytical gradient. Okay, go here, gradients, and see that you can compare. So even that we have a very good agreement in the T field, when you approximate gradients, is here where you have problems. And this is important part in the numerics, and this is where we're pushing more now when you look at the discretization dictionary settings. Here, all these corrections, these methods, these are different methods to compute in a different way. Now, to approximate the diffuse term, then you have different methods to compute gradients. And this is a correction, okay, that is experimental just to avoid to have unbounded gradients. So usually it's more important to look at gradients than looking at the actual solution. So here you can explore everything. Okay, so let me go back analytical solution here, and here let me go also. So see that analytical solution seems to be very, very good, but then when we approximate gradients is where we start to have differences. This doesn't mean that this is wrong. This is just the numerics. If you have a better mesh, finer mesh, you will be closer to what is the analytical solution. Okay, so this was this case, and let's move to the last case, which is the Fluvio Laplace Cursor. Okay, so this is a type of mesh that you start with an orthogonal mesh, but then you add skews, Nisbet, and non-orthogonalities. Just to run, it is exactly the same, nothing changed. Fluvio, and see that now it's taking more iterations. See that 12 iterations, you have minimum and maximum values. Okay, so this is the verbosity level. Let me show you. Let me go here and close. Okay, so always readme, you want the instruction, you will have here, and then settings have there. So as you go, when you look at the simulation controls, this verbosity low, you see less information on the screen. So here you have it at the maximum level, which is good to have this. So see that you have all the iterations, no orthogonal iterations, starting iterations, initial, final residuals. Okay, so for instance, if you increase the number of orthogonal corrections, okay, so these are the corrections to improve the approximation of the diffusive fluxes. So see that you see all your corrections here. So Okay, now let me go and change method, because just to show you that the over-relax method is in theory and literature, you will see that is the best method. But let me use in this mesh orthogonal correction. Okay, so this is okay, but it's not so good when you have bad quality meshes. And see that here is going to a maximum number of iterations, but see that minimum and maximum values what you have here. So in theory, this one is diverging. So just to show you, now let me compare the fields. Okay, and we have 100 iterations. So it's converting everything. And let me go part view. And open Postprod, BTK fields, open everything. You have here all the fields, you can visualize the mesh and look at the mesh. So let's see, the problem here is that you have now too large transition. Here you are mirroring the gradients, but also you have large orthogonality skewness. And this gives problem to numerical methods, okay, to approximate those gradients, okay? So there are all these methods, different corrections. Oops, okay, let me open again, part view. And if I go Postprod, here fields, and see that at the beginning, okay, it seems that it's convergent, but see that now you have problems here where you have here the large aspect ratio transition between all the cells of different dimensions, up to the point that now it diverges and goes out of control. So to control that one, for instance, there are many ways to control that, okay? So you can increase the number of orthogonal corrections. In this case, whoops, okay, so with this, in this case, it will help a little bit, but at the end, it will always diverge. See that it's already diverging. Okay, so here you have different methods, but the best method, when you use this one, this is the method that it works fine, okay? So we can go here and we can use this for the moment, experimental option, you put it to 0, okay? So this is a limiter to avoid, note that the diffuse stir increase too much. And this one, it helps a lot, but it is not okay. It added too much diffusion, okay? So be careful, you need to understand first what is going on there, okay? But for the moment, we don't recommend you to use, we recommend to use the over-relax. Then you can also play with different ways to compute the gradients, okay? And so on. So this is how it works, okay? So let me go here, Fluvio-Poisson, okay? We have a good solution. Let me convert it, okay? First, let me clean, because already I had the previous solution. Oops, okay, no. Sorry, clean, let me run. So we have 12 iterations, so be careful here. Okay, launch part of it. Postprod, BTK fields, open there. And now here you have solution, and you can go one slide at a time and see that now this method is working very well, keeping all the gradients, everything, keeping everything bounded. But there is some diffusion, okay? But just to show you that even in such a simple example that you have the Poisson equation that in theory is a smooth operator, if you don't have good quality meshes, you will diverge. But also there are some corrections, some methods that you can access here in your input files. So using the right methods also will let you converge, but have in mind that you are adding numerical diffusion. So you can go to the source code and read all the implementation. Remember, this is standard theory. So with this, I think I will stop this first tutorial. This is the serial one. The next tutorial is exactly the same. I'm just going to focus in the Examesh, but just to show you how to run in parallel. So thank you for your attention. See you next time. Bye.